Welcome to Tomorrow Unveiled. Today we're diving into something that honestly sounds a bit like science fiction, but it's happening right now. We're calling it green code hot core.
It's a really exciting convergence.
Exactly. It's where this cutting-edge digital stuff, the green code, meets these incredibly powerful clean energy sources, the hot core. Think advanced nuclear fusion, maybe even breakthrough energy storage.
And this past week was, well, it felt significant, didn't it? More than just small steps.
Definitely. It feels like a real shift. And it seems to be driven by this almost unbelievable energy demand from artificial intelligence.
Which is soaring. I mean, truly soaring.
Right. And the twist is, AI isn't just gulping down power, it's also becoming this key tool to actually accelerate the development of these very energy systems. It's fascinating.
A real feedback loop starting to form.
So our mission today on Tomorrow Unveiled is to unpack what happened this week. We'll look at the breakthroughs, some major commercial deals, and this changing landscape that might signal a whole new era for global energy.
And we'll be drawing on the findings, themes, and data points our dedicated research team pulled together, really looking for what's corroborated across different sources this week.
Okay, let's get into it. First up, how is this green code, how is AI actually making the dream of limitless energy, like fusion, happen faster?
Well, this is where things get really interesting. The role of AI in speeding up fusion research is becoming quite clear.
How so?
Our analysis of the information highlights a really big development from one of the leading national labs. They've built a deep learning model, an AI, that can predict whether these incredibly complex fusion experiments will actually work, and with remarkable accuracy.
Predict success. For fusion, that sounds huge.
It is. Take a key experiment back in 2022, an inertial confinement test.
Yeah.
Where they blast tiny fuel pellets with powerful lasers.
Right, trying to get ignition.
Exactly. This AI model predicted success for that specific test with 74% confidence. And guess what?
It worked.
It worked. The prediction was proven correct later on. And crucially, this isn't just statistical pattern matching. It's what they call physics-informed AI.
Physics-informed? What does that mean?
It means the AI doesn't just look at past results. It understands the underlying physics principles. It integrates huge amounts of experimental data, simulation outputs.
Got it.
And that allows the scientists to effectively pre-test their designs, to de-risk them before committing the massive resources needed to actually run the experiment.
Wow. So it saves potentially vast amounts of time and money.
Immense amounts. It's starting to shift fusion research away from what was often, a kind of brute force trial and error process. It's becoming much more targeted.
That's incredible, like giving them a much clearer roadmap through incredibly difficult terrain.
Precisely.
But here's where it gets even more tangled, maybe. This green code, the AI itself, needs staggering amounts of power.
Right? Oh, absolutely. The demand is enormous and growing exponentially.
So the very tool accelerating clean energy research is also driving the demand that's reshaping the energy market itself. What does that mean for the hot core side, for the actual energy generation?
Well, that huge energy appetite from AI and data centers, it's directly triggering major commercial moves. Companies need secure, reliable, 2037 clean power.
Not just clean, but firm power. Always on.
Exactly. Unlike, say, basic web hosting, these advanced AI computations can't tolerate fluctuations. They need constant, high-quality power.
And that need is pushing investment.
Directly. Our research team has tracked significant investment flows, speeding up the deployment of these high-density power sources. It's not just a nice-to-have anymore. For these tech companies, it's becoming a core business necessity.
And we're seeing some massive bets being placed, particularly on advanced nuclear, aren't we? Some really headline-grabbing deals just this week, according to our sources.
Indeed. One of the biggest announcements involved a major U.S. utility. They signed a power purchase agreement, a PPA, to buy up to 50 megawatts of electricity from a Generation Savi nuclear reactor. Specifically, the Hermes 2 reactor from Kairos Power.
And who's getting that power?
A leading tech company is getting the clean energy attributes, basically the credits, for its data centers. It's a public-private partnership structure.
And what's special about this Hermes 2 reactor? Gen 5 sounds advanced.
It is. It uses molten fluoride salt as a coolant, not high-pressure water like traditional reactor.
Ah, so lower pressure.
Much lower pressure, but very high temperature. That inherently boosts safety, less risk of pressure buildup, and increases efficiency because of the high heat.
And the timeline.
They're targeting operations for 2030. which in the world of nuclear development is actually quite soon.
That is pretty quick. And that wasn't the only major deal-making waves, was it? Our research flagged another data center operator making an even bigger move.
That's right. This one was really notable for its scale and its diversity. A different data center operator announced deals to secure over 1.2 gigawatts. That's 1,200 megawatts of power.
1.2 gigawatts. That's a huge amount of power.
It is. And significantly, it's coming from a portfolio of different advanced reactor developers.
A portfolio, so not betting on just one horse.
Exactly. It's a smart strategy.
Yeah.
It spreads the technological risk across several different novel reactor designs. Some might come online sooner, some later, some might face hurdles. It builds a more robust pipeline.
That makes sense. Can you give us a quick snapshot of the kinds of reactors in that portfolio? What makes them innovative?
Sure. It's quite a mix, which is what makes it so interesting. Our team identified several key ones.
Okay.
First, there's Oklo's Aurora reactor. It's a fast reactor.
Fast reactor, meaning?
Uses fast neutrons. And its really unique feature is that it's designed to potentially run on existing nuclear waste as fuel. So it could actually help reduce the waste stockpile, aiming to close the fuel cycle.
Wow, okay. Using waste as fuel? What else?
Then there's Radius Colados. This one's a microreactor. Think small, transportable.
Like truck-sized.
Pretty much. Designed for rapid deployment, maybe factory mass production. In fact, there's already a contract for one to power a U.S. military base, aiming for 2028. So that shows a very near-term application.
Interesting. Military bases need reliable power.
Absolutely. Then you have the Rolls-Gorges SMR. That's a more conventional pressurized water reactor design, but scaled down to 470 megawatts electric.
SMR meaning small modular reactor?
Correct. And its key innovation is being optimized for modular construction in a factory. The idea is to build most of it off-site, ship it, and assemble it quickly, cutting down those long construction times and costs that have plagued traditional nuclear builds.
Streamlining the process.
Exactly. And finally, there's a really advanced concept in the mix. Stellarius breed and burn molten salt reactor.
Breed and burn, that sounds intense.
It is, conceptually. It's designed to actually breed more fuel than it consumes as it operates, potentially running for decades without refueling. And while doing that, it could also consume or burn existing long-lived radioactive waste products.
So incredibly long operation and waste reduction combined.
That's the goal.
Yeah.
It's further out technologically, but it shows the breadth of innovation being pursued. Each of these represents a real step change.
It really feels like a genuine renaissance for advanced nuclear, driven by this practical need for power.
The market pull is definitely there now.
Okay, so nuclear is getting a boost. What about the other critical piece for a clean grid energy storage? Any movement there?
Yes, definitely. The hot core idea isn't just about generation. It's also about storing energy densely. And our research team flagged a potentially major breakthrough here too, this one coming out of a university in China.
A battery breakthrough. We hear about those often.
Well, this one seems particularly significant, though still early stage, of course. Researchers there developed a lithium battery that achieved an energy density over 600 watt-hours per kilogram.
600. What's typical now in, say, an EV?
Good current EV batteries are maybe around 250 to 300 weight kilograms. So this is essentially double.
Double the density. That would mean double the range for an EV, potentially.
Or the same range with a much lighter, smaller battery. But what's maybe even more impressive is its stability and resilience.
How so?
According to the reports, it remained stable over many charge cycles. And get this, it didn't ignite even when exposed directly to an open flame.
Wow, that addressed a major safety concern with lithium batteries.
Big time. And it also apparently worked well at extremely low temperatures down to minus 60 degrees Celsius.
Okay, that's impressive versatility. But you said early stage.
Yes, it's a lab-scale proof of concept. Scaling up new battery chemistries is always a huge challenge. But if it proves scalable and cost-effective, it could be revolutionary. Radically longer EV range, much safer grid storage. It's a material science leap.
Definitely one to watch. Okay, all this sounds incredibly promising for sustainability, advanced nuclear, better batteries. But let's talk real-world implications. What are the benefits beyond just clean power, and what hurdles are still in the way?
Well, looking at the bigger picture, the sustainability angle for these high-density solutions is really compelling. Think about land use.
Right, solar farms and wind farms can take up huge amounts of space.
Exactly. These advanced reactors, especially the SMRs and microreactors, provide reliable 247 power from a tiny physical footprint compared to intermittent renewables generating the same annual energy. That drastically reduces land use conflicts.
And you mentioned repurposing infrastructure.
Yes, there's real potential to site these SMRs at former coal-fired power plants. You can reuse existing grid connections, maybe some buildings, and crucially, offer a just transition for the workforce.
Keeping those skilled energy jobs in the community.
Precisely. Retaining skilled workers who already understand power generation, just shifting the technology, that's a powerful social and economic argument.
Okay, but let's tackle the elephant in the room for nuclear. The waste. That's always the sticking point, isn't it?
It absolutely is. And it's a valid concern that the industry has to address head on. But what's interesting is how innovation is tackling this now, trying to turn the problem on its head. Our research team highlighted a couple of fascinating new approaches. One collaboration is looking at using repurposed plutonium material recovered from legacy nuclear waste to actually create fresh fuel for some of these advanced reactors.
So using existing waste to power new reactors.
Effectively, yes. Another concept involves using particle accelerators. The idea is to bombard spent nuclear fuel, not just to neutralize it, but to generate tritium.
Tritium. Isn't that needed for fusion?
Exactly. Tritium is a rare and essential isotope for many fusion reactor designs. So this could potentially kill two birds with one stone, reduce the hazard of spent fuel, and produce a crucial resource for fusion energy.
That's clever. But does this solve the long-term storage issue?
Not entirely. A permanent deep geological repository for the remaining high-level waste is still seen as necessary by most experts, and that remains a major political and technical challenge globally. But these innovations show a much more proactive approach. Instead of just storing waste, they're looking at closing the fuel cycle, reducing the volume and longevity of the waste, and even extracting value from it. It's a different mindset.
A more circular approach.
Yes, exactly. Less linear, more circular.
It's also just striking that the green code, the AI doing all this amazing research and design work, is itself so power hungry. You mentioned the feedback loop earlier. It feels like a snake eating its own tail sometimes.
It really does create a powerful dynamic.
Yeah.
Those AI models speeding up fusion research, they often run on the world's biggest supercomputers, which consume electricity like a small town.
Right.
So there's this direct, undeniable link. The computational tools driving clean energy breakthroughs are simultaneously escalating the energy demand that makes those breakthroughs so necessary.
So the ideal future is?
The ideal future, as envisioned in some of the material we reviewed, is this tightly closed loop. You have next-generation, highly efficient AI data centers running entirely on clean, firm power, likely from advanced nuclear or maybe future fusion reactors. And inside those data centers, they're hosting the very AI models needed to design the next generation of even safer, more efficient, more sustainable reactors.
A virtuous cycle powered by clean energy itself.
That's the vision, using clean power to create better clean power.
So, thinking about the broader energy mix, how does this hot core revolution sit alongside the progress we're still seeing in traditional renewables like wind and solar? Is it one versus the other?
I don't think it's really a competition. It feels more like a strategic rebalancing, a maturation of the market.
How do you mean?
Look, low-density renewables like solar and wind are still growing fast. Reports indicate the U.S. solar sector aims to add something like 33 gigawatts this year alone. China just put up a massive 17-megawatt floating wind turbine, a world record. That progress is real. But they're also hitting some predictable growing pains. Our research flagged consistent themes. Policy uncertainty causing project cancellations worth billions, difficulties getting financing as interest rates rise, increasing local opposition to large land footprints.
NIMBism, not in my backyard.
That's part of it. And also grid limitations. Sometimes there's so much solar or wind power generated it can't all be used, leading to curtailment. These are all inherent characteristics of intermittent sources that depend on the weather and require significant grid upgrades and storage.
Okay, that makes sense. We love hearing your thoughts, by the way. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this green code hot core dynamic. Is this the future?
Definitely interested in hearing perspectives.
And if you're finding this insightful on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe hit that notifications bell so you don't miss our future deep dives.
It really helps get the word out.
So back to this rebalancing. What's fundamentally driving the shift towards high-density power now? Why are these big deals happening this week?
I think the commercial strategies we saw emerge this week really signal that the energy market is getting more sophisticated. The focus is shifting.
Shifting from what to what?
From simply buying the cheapest available renewable megawatt word, often wind or solar when the sun shines or wind blows, to securing a reliable 247 supply of clean megawatt hours. It's a subtle but crucial difference.
Megawatts versus megawatt hours, capacity versus actual delivered energy over time.
Exactly. Big, sophisticated energy buyers, especially these tech companies with mission-critical data centers, are now pricing in the hidden or maybe not so hidden system costs of intermittency. The need for massive amounts of battery storage to cover gaps, the cost of grid firming services, the necessity of keeping backup generation on standby. When you add all that up, the levelized cost of intermittent renewables plus storage and firming starts to look different.
So the fact that companies are willing to sign these complex, very expensive, long-term contracts for advanced nuclear.
It demonstrates that the total all-in cost of getting reliable 2047 clean power is the metric that matters now. It's not a rejection of solar and wind, they're vital for decarbonization, but it is a recognition of their limitations for powering things that absolutely cannot shut down.
Reliability is becoming paramount.
Especially for the digital infrastructure underpinning our economy.
Okay, let's talk timelines again. You mentioned 2030 for that Kairos reactor, 2028 for the Radiant Microreactor. These advanced fission technologies seem to be getting quite concrete.
They are. Several SMR developers are targeting first commercial operations in that late 2020s, early 2030s window. Getting those first-of-a-kind units built and operating is a crucial next step.
What are the main hurdles to scaling up after these first units, going from 1 or 2 reactors to whole fleets?
There are several big ones. First is regulation. We need streamlined, predictable regulatory frameworks specifically designed for these advanced reactors, not just applying the old rules built for giant bespoke plants. Moving away from site-by-site, one-off approvals is key.
Making it more standardized.
Yes. Then there are supply chain challenges. Some of these reactors need specialized fuels, like HAU, high-assay, low-enriched uranium, which isn't produced at scale yet. Ramping that up is critical.
Fuel availability.
And finally, there's public acceptance. Building trust and demonstrating the safety and benefits of these new designs will be essential for widespread deployment. It's a significant industrial lift.
And what about fusion? Still the ultimate prize? Maybe you said AI is speeding things up, but it always seems to be just over the horizon. Has that fundamentally changed?
Fusion. Well, it remains a multi-decade grand challenge, let's be realistic. AI is definitely accelerating the R&D, helping solve complex physics problems faster, optimizing designs. But getting to a commercially viable prototype reactor, one that reliably produces net energy and can form the basis of a power plant, that's still likely in the 2040, 2050 timeframe at the very earliest, according to most projections our team reviewed.
Still decades away for commercial power.
Probably. The main bottlenecks are now shifting from pure plasma physics controlling the superheated fuel to immense engineering and materials science problems.
Like what?
Like developing materials that can actually withstand the intense heat and neutron bombardment inside a working fusion reactor for years on end without degrading. That's a monumental materials challenge, though AI is helping model potential solutions there too.
So fusion is still a longer-term play, while advanced fission is moving towards commercial reality much sooner.
That seems to be the consensus, yes.
Okay, so pulling this all together, what's the main takeaway for you, the listener, and maybe for policymakers or investors tuning in?
I think the biggest message from this week's developments is this clear shift from technology push, where developers try to sell their new reactor concept to market full in the advanced nuclear sector.
Meaning the customers are now actively demanding it.
Exactly. Big, credible buyers are signing real contracts. So for investors, the focus should be on companies that have clear paths to commercialization, strong engineering, and these bankable partnerships. It's less speculative now.
And for policymakers.
The urgent need is creating those stable, predictable, and efficient regulatory pathways, specifically for advanced reactors. Cut the red tape where it's safe to do so, standardize processes, perhaps provide loan guarantees or other financial support to de-risk those crucial first projects. Treat it like the critical infrastructure it could become.
Makes sense. And for industries needing lots of power.
For energy-intensive industries, manufacturing, chemical production, and of course data centers, advanced nuclear is really emerging as a serious strategic option. It offers deep decarbonization and long-term energy security, moving away from reliance on volatile fossil fuel prices and the limitations of purely intermittent renewables. It's a viable third leg for the stool.
A really powerful combination of factors converging.
Absolutely.
So as we wrap up this deep dive on Tomorrow Unveiled into Green Code Hot Core, it really does feel like we're at a pivotal moment. This interplay between AI's capabilities and its energy needs is fundamentally reshaping the path forward.
It is. And that strategic rebalancing we talked about towards valuing reliable 247 clean power alongside maximizing cheap intermittent generation suggests the future grid won't be monolithic.
A mix of technologies.
Exactly. A truly resilient, fully decarbonized energy system will likely need an optimized blend, high-density sources like nuclear providing the backbone, low-density renewables like solar and wind, contributing vast amounts of energy when available, plus storage and smart grids tying it all together, each playing to its strengths.
And the breakthroughs just this week, AI predicting fusion, next-gen reactors, getting commercial contracts, those super dense batteries, they really suggest we're making tangible progress towards that future, maybe faster than we thought.
The pieces are definitely starting to fall into place.
Okay, before we go, a quick reminder for our audio listeners. If you're enjoying Tomorrow Unveiled on Apple Podcasts, Spotify, or wherever you listen, we'd be incredibly grateful if you could take a second to leave us a rating and review.
It genuinely helps new listeners discover the show.
It really does. So here's a final thought to leave you with, something to mull over. If AI's massive appetite for energy is perhaps unintentionally accelerating technologies like advanced fission and fusion, what other incredibly difficult, maybe even seemingly distant scientific frontiers might suddenly get fast-tracked into reality because AI needs the power or the compute to make them happen? What else might this energy demand unlock?
That's a fascinating question. The unintended consequences could be profound.
Something to think about. Thank you for joining us on Tomorrow Unveiled. We'll be back next time with more insights into the innovations shaping our world.